All right, guys. If everyone can settle down, we're going to get started. So this is exam 1 stuff. So long time ago. Hopefully most of you guys remember some of it. If not, that's why you're here. It's not going to take long. It'll probably take about an hour and 10 minutes at most. So you guys can go enjoy the nice weather outside. I know I want to. All right. So we're going to cover a bunch of stuff. We're going to cover separable, good old separable, exact, linear, the Bernoullis, and the beginning of homogeneous, homogeneous, however you want to say it, which most of you guys should know from doing it a lot of times, repetition. Good stuff. All right. So without further ado, let's get started. And once again, if you have any questions, please do not hesitate to ask. And just raise your hand, call my name. I'm Pat. So just, yeah, we're going to start. All right. So separable, basically you separate variables. And then you have a dx on one side, a dy on one side, on the other side. And then you integrate both sides. And then you add a c to the side with the x's. And then you find y. And that's your answer. So we're just going to go right ahead and do a simple example of that. All right, so we're going to have dy dx equals sine squared x. I don't know if that's a good idea. I don't want to integrate that. I didn't do that example out. I just have it here. I'm like, why did I write that? All right, this is better. So y times the sine of x over 1 plus 2y squared when you have an initial condition, which is y0 equals 1. The initial conditions, don't panic, because those you just put in at the end to find the plus c or wherever the c might be. It should be, right? Yeah, good call. I'm off to a good start, right? All right, so dy dx, and your initial condition is y of 0 equals 1. All right, cool. So we have variables, right? First thing to recognize is that it is separation of variables. The way you recognize that is, well, really for any of these first-order differential equations, whether it might be linear, Bernoulli, or exact, or separable, the first thing to look for is separable. That's the easiest one to do. And the way to look for it is you see if the y's and x's are indeed separable. So these ones you have y times a sine of x, so that can be separated. And then you have this whole monomial term in the bottom, where you have 1 plus 2y squared, which that whole thing could be put in parentheses and separated for y. And then you have equals dy and dx, which those can indeed be separated. All right, so let's separate that. Suppose we moved this 1 plus 2y squared over to the other side. We end up with y times the sine of x equals 1 plus 2y squared dy dx. And now we want to move this dx to the other side. So then we could, I'll go down, we have sine of x times dx equals 1 plus 2y squared dy. And then you have a y right here. So now we want to take this y, we can just divide it by the side and put it on the bottom of there. And voila. You separated your variables. So first step is done. Now, next job is you have a dx and you have a function in front of it, a dy and a function in front of it. Our job is to integrate both sides so we can find our function. So let's do that. The right side we'll leave for the second part. So integral of sine of x is going to be negative cosine of x. Good. So negative cosine of x is just going to be like that. Negative cosine of x. And then you have to add a plus c. It's always good to, you can add the plus c to either side once you integrate it, but I would recommend adding it to the x side, because once you're here, you could just like, it's just easier, whatever. I'm not going to explain. It's just easier. Just add it to the x side. All right, so you have that for the x side. Now, with the right side, we have the integral of that. So you could do that by, let's see, you could do a u sub, because you have y squared, and you have a y right here. You can make u equal y. Or no, u equal y squared, 2y. You can make u equal this whole thing. Or another method you can do is to break this up into 2 fractions, which I'm going to do. So let's take this integral, rewrite it. That's not an integral. It's a straight line almost. All right, that's an integral. I can't draw integrals really well. All right, so we're going to break this up into 1 over y, the integral of 1 over y dy, plus the integral of, so since we do 1 over y, and then we have plus 2y squared over y. So this 2y squared over y, the y's would cancel out. So you'd end up with just 2y. So the integral of 2y dy. So now this is going to equal, so the integral of 1 over y dy is going to be what? I didn't hear anybody say it, but natural log. So good, natural log. So you have natural log of y. Now the second part, really easy, just 2y integral of that is just going to be y squared. So plus y squared. And that's going to be the right side. So we're going to make this equal to the left side, which is negative cosine of x plus c. I'll just put like an arrow pointing to this. So this is our answer, right? This is our answer without putting in the initial condition. And another thing they might ask is like, well, it's a really common mistake. People don't know what implicit or explicit means. So if it means explicitly in terms of a certain variable, such as explicitly in terms of x, you have to put y equals something in terms of x. But something like this, where you have an ln and a y squared in the same part with the y, you can't really have it explicit in terms of one variable. So this is an implicit solution. So yeah, or if you have like natural log of xy, or like these x's and y's like intertwined, and you can't really separate any of them any further, that would be an implicit solution. So this is a good question would be like, is the solution implicit or explicit? So this would be implicit because it's not y equals, like the standard form of y equals something in terms of x. So once we have this, we can use the initial condition of y of 0 equals 1 to solve for the constant c. So if you put y of 0, okay, I was about to say put 0 into there, that would be undefined, that'd be crazy. But we have, it's equal to 1. So we're going to put in y of 0 equals 1. So that means we're going to put in 0 for x and 1 for y. So if we put in 1 for y here, natural log of 1 is equal to 0. So 0 plus 1 squared is going to be 1 equals negative cosine of 0. Cosine of 0 is going to be, according to the unit circle, is going to be 1. So it would be negative 1 plus c. Bless you. So now the 0 goes away. So you have that. You add 1 to each side. Or I add 1, add 1. So 2 equals c. OK, so now we know that 2 equals c. We simply just get rid of the c and put a 2. And that is your answer for separable. Is there any questions on separable? Do you want me to not do separable anymore and just go on? Next one. Yeah, because I feel like you guys pretty much got this. I'll move it up in case you guys still need a copy. If you have any questions at the end, I'll stay for a couple more minutes, maybe do another example if you guys want for separable. So now we're going to move on to exact. So exact is a little trickier because you got to memorize more stuff in terms of like memorize that there's an m and an n and which one goes with which variable and what to do with that. It's kind of like a stepwise process, more than separable is, because separable is kind of straightforward and makes a little more sense. So for exact, maybe I should bring this board down. Cool. All right, so exact. Bless you. All right, so for an exact equation, all right, so the first step to do is your first step you need to do is verify whether the equation is indeed exact. And the way to do that is you have two parts of the equation. A part where there's going to be a polynomial with a dx and a polynomial with a dy. And the idea is that you need to mark the polynomial that's with the dx as m and the polynomial with the dy as n. And then you take some partial derivatives and all that fun stuff and see which ones and see if it works. I'm not going to just, I'll go through it right now. I'm not going to just talk about it because it's kind of difficult if you talk about it. All right, so here's an example. So 3x squared plus y squared minus 2 dx plus 2xy plus 6y minus 3 dy equals 0. OK, so like I just said before, everything that has the dx in front of it, or in back of it. So this whole polynomial term, or big monomial, I don't even know what that is anymore, polynomials and monomials. This whole term, this is going to be your m. So everything with your dx is going to be your m. That's good to know. So m. And then everything with your dy is then going to be your n. All right, so once you have this association, the idea is to check if it's exact. So in the checking if the equation is exact, usually you have your association with m and dx and n and dy. This is where you're going to flip-flop those associations. So you're going to take the partial derivative of m in terms of y and see if that partial derivative is equal to the partial derivative of n in terms of x. So this is the only place in the entire process of this equation, of this process, I don't know, that we are going to switch those associations between m and x and n and y. So let's go ahead and check if this is exact. So we're going to take the derivative of, well, I'll even write this, to check dm dy. I'll put equals and then a question mark on top of it, dn dx. Just like that. All right. Wait, is that right? Yeah, OK. All right. I was like 80% sure because I haven't done this in a while. All right, so dm dy. So let's just take the partial derivative. If you find a partial derivative of that, you're going to get, since this is just x's, it's going to go away. This is going to become 2y, and this is going to go away. So you have 2y equals, and then here, partial derivative of n in terms of x, you're going to have 2y there. And then this is going to go away because there's no x's, and this is going to go away because there's no x's. Oh, so look, it's exact. That's cool. Sometimes it might not be. Sometimes it might be like, it just won't work. And then you guys will freak out, oh my god, I want it to work. And you'll try to do it anyway, but you'll end up at a dead end, and it won't work. It might be something else, though. It might be linear. They might be like, you might have to manipulate this a little bit and make it linear somehow, but don't freak out about that, because that might not happen. I'm just trying to scare you. All right, so the next step is, I don't need this. OK, the next step is we need to try to find, just like in everything, like I said yesterday a lot of times, in differential equations, we're looking for the template of the answer, so what the answer is going to look like at the end. And we need to end up plugging some stuff in later. So another thing to know is that the function itself, or the partial derivative in terms of x of the function is equal to m. And the partial derivative of the function in terms of y equals n. That's where your association with m and x and n and y comes from, that this is true. And who made this true? I don't know, some scientist back in some mathematician back in the 1700s, I don't know, that made this true. But this is true. So from this, this is where we derive our steps from. This is what guides us into what we do next. So what we're going to do next is we have m. We could find the integral of m in terms of x. So if you integrate both of these sides, integral of m in terms of x, you're going to get f. So let's do that. You're going to get a template of f. You're not going to get f exactly. You're not going to be done after that. You're just going to get a template of what x is, or f is going to look like. So let's do that. So we're going to take the derivative, or the integral, sorry, of m dx. So I'll put step 1. Or that's really step 1, but step 1 of actually solving it. So the m dx is going to be the integral of 3x squared plus 2y minus 2 dx. All right, so let's solve that integral. That one's pretty easy. This is simply going to be x cubed plus y squared x minus 2x. Now, in every integral, what do you need to forget? Some people always forget the plus c. You always need to add the plus c. But in this case, the plus c is a little different than just a constant. Because when you're taking a partial integral in terms of one variable, such as partial derivative of x, partial integral of x, there's still going to be the other variable, y in this case, that's held constant. So from here, we're not integrating this y at all. We're just taking this partial integral in terms of x. So if that's the case, you're going to have two things that could be constant. Numbers, which are always constant, and your variable that's held constant in this partial integration, which is going to be y. So if that's the case, that means the constant that we're going to add could also be a constant, or it could be any function of the other variable that's held constant, which is y. So we represent that by adding a g of y. So this g of y could either be some function of y, obviously, or it could just be a constant like any other. It could be 2, it could be 5 million. Who knows? That's what we're trying to figure out. So from this first step of integration, we found the template of f of xy. So this is our answer, and our next steps are going to be to find this g of y. So let's do that. So to find the g of y, we can So since we know, well, we have this already, we use this association. We could use the second association of df dy equals n. So that means we have f. If we go back and derive it this time, but in terms of y, we can get n. And we can get this n to try to equal this n, and then see what's similar and what's different, and try to find that g of y. So let's derive this in terms of y. So df dy equals, so this would go away. This would become 2yx. This would go away because it's just x's. And this g of y, would become g prime of y. So plus g prime of y. All right. So according to our associations that are very important, I'm actually going to put these in a box, because everything in a box is important, right? So so our df dy is equal to this. Our df dy is also going to be equal to n, which n is everything that's associated with y. So that's our 2xy plus 6y minus 3. So we can go ahead and make that equal. That's going to be 2xy plus 6y minus 3. All right. So from this, you can see that things cancel out. A lot of the times, at least one thing will cancel out. If it doesn't, you might have done something wrong. You might go back. You should go back and start from here and try to see if you integrated or derived wrong, because something should cancel out. You shouldn't end up with g prime of y equaling a whole bunch of terms with ln's and cosines and a lot of crazy stuff. So this is pretty simple. This 2yx would cancel out with this one, and you're left with g prime of y equals 6y minus 3, which is pretty simple. OK, so g prime of y, that's a cool looking g. OK, equals 6y minus 3. All right. All right, so 6y minus 3. Now, to find our g of y, because we're looking for this g of y, we have g prime. We could just integrate that in terms of y to find g of y. So let's integrate both sides. So I'm going to write an arrow here. So the integral of 6y is going to be 6y squared over 2, or simply just 3y squared minus 3y. And then you add a plus c. Now you add the plus c here because you're integrating in terms of one variable. So the constant after the integration is always going to be a plus c, always going to be some number constant. So you have that. Now this can become I need an eraser. This is always going to be 3. OK, so there is your g of y. G of y. OK, so now we can just take out this g of y, and we're going to put in 3y squared minus 3y plus c. All right, so that's the complete answer. If we did have an initial condition, which I don't think we do, we would plug in, we'd have f of xy, or just f of something equals, or you'd know what x and y is, and you know what this is. You just need to find c. So that's how it is. Any questions on exact? No? OK, good, good. So do you guys want me to do another exact, or you want me to move on to linear and Bernoulli? Move on? OK, OK. All right, so I'll move this one up. Bring this one back down. And I'll erase this. So it's going to be really quick. We're almost like halfway done. So what was that? It felt like 10 minutes. It was like 20 minutes? 21 minutes, yeah, OK. 20. All right. So next thing we're going to do, so we're done with separable, done with exact. OK, so now we're going to do linear. So linear is another process, another thing where you have q of x, p of x. You have a whole bunch of stuff going on. So let's try to make it make a little more sense out of it. All right. So without even doing anything, without even having a problem, I'm gonna show you what's going on here. So a linear equation looks like this. It looks like dy dx plus p of x times y equals q of x. So you're going to have, or if you have a suspicion of something being linear, you need to make it in the form of this. if you have a 2 in front of here or some constant, there's some in the, I think the book, they have it like this, where you have some function or some anything times the dy dx in the front, the coefficient of the dy dx. This you need to divide out. So you need to divide this, and then you'd have your new p of x and your new q of x after you divide the a of x over. But we're going to assume there's nothing there. I mean, there might be. In a lot of example problems, there is something there. But it's easy to just divide out. All right. So once you have this, our job is to solve the differential equation. So here's how to do it. So the first step is going to be, you need to find your integrating factor. Who knows what that is? It's mu, right? Some guy just made it up. Mu. It's just mu, right? So what is mu? So mu of x, it's going to be another function. It's going to be e to the integral of p of x dx. All right, so that's it. That's the definition. So you'd find a lot of times you'd have an ln up here, or a lot of times you'd have like p of x would be 1 over x. Integral of that would be natural log of x. E to the natural log of x is 1, or some factor. So it would end up being like a constant sometimes, or just an x, or something really simple. All right, so make sure you do that correctly. So then the second step is to multiply mu of x by, or multiply mu of x, I'll just put throughout. So that means multiplying mu of x by the entire starting equation. So that means if there is a coefficient in front of here, after you divide it out, that would be your starting equation. OK, so once you multiply mu of x, so you'd have mu of x times your dy dx plus p of x y equals q of x, like that. Once you divide it through. So after you divide it through, you can just, they never explained this rule to me correctly of how this even works. But you just assume, and it works. It works, I don't know how though. But it works that the left side of this equation, once multiplied by mu, is equal to the derivative of mu times y. So like of just mu times y. So you could just say that this new left side of the equation is going to be equal to mu of x times y, or the derivative of it. Derivative of mu of x times y. Just like that. And how, why, I don't know. But that's just a good thing to know. I'll say that again once we do an example. And this is still going to be equal to the right side of this equation, q of x, times mu of x. So mu of x, q of x. All right, so then the next step would be to integrate both sides. Because we want to find this y, or get this out of the derivative. And then we're going to divide this mu of x over here. So we're going to integrate both sides. We integrate this. We take the integral of a derivative. So that's going to cancel out. This cancels out, and you end up with mu of x times y. That's it on the left side. The right side is going to be whatever the integral of this is. And then once you have this, mu of x times y equals the integral of mu of x times q of x, you can simply just say that you divide mu of x by both sides. This is your answer. So you're going to have y equals all of that. So without even doing an example problem, we found what the answer is of anything, of any one of these linear equations. So all you need to, well, I would suggest do all the work. Do all the work. But if it's like 10 minutes left of the 4 hours, I don't know how you would stay through that for that long. But suppose there's not much time left, or you're panicking, and you don't know what to do. You just know how to get to here, and everything gets fuzzy. Remember this, that y is equal to the integral of, you just go right, once you find mu of x, you're done. Because you can just do integral of mu of x times q of x over mu of x. And that's it. So, OK, any questions on that? Now we're going to do an example. We're going to go through the entire process with an example. OK, I'm going to do that on this side because I'm conserving room today because this isn't as hectic as yesterday. OK, where's an example? All right. All right, so example, dy dx equals 2y over x plus x squared cosine of x. We have an initial condition. That is y of pi equals 2 pi squared. All right. OK. So the first question that we need to ask is that, is this linear differential equation the form of the normal linear equation that needs to be, this form? Answer is no off the bat. But we need to rearrange this for it to look like that. So we could do that. We need dy dx plus or minus something times y. So here we have 2y over x. So we have 2 over x is going to be equal to our p of x. So you can already see that. So we can move this over to the other side. So we have dy dx minus 2y over x. And this is going to equal x squared times cosine. OK, so now it looks like it's in the form of our linear. OK, so next step, find p of x and q of x, locate these two functions. So we found p of x right here. Make sure you don't forget if there's a negative in front of here. Make sure you include that negative inside the p of x, because the original form is plus p of x. So if you have, just like this, you have minus 2 over x, that will be your p of x. So let's write that down. So p of x is going to equal negative 2 over x. So it's everything in front of the y, including the negative. OK, q of x, we could just say it's right there, whatever. And p of x right there. So now, next step is to find our super awesome special integrating factor. All right, so our integrating factor is going to be equal to e to the integral of our p of x. So p of x we just found. So we could do e to the integral. We could take the negative out. 2 over x dx, just like that. OK, so once we have this set up, we can actually solve this because we're not dealing with an example. We could actually solve this out. All right, so this is going to equal e to the negative. So now the 2 can come out also, and then you could also have the integral of 1 over x, which is going to be natural log. So you're going to have 2 times the natural log of x dx. Or not dx, we already found it. OK, so this is your integrating factor, right? Looks kind of complicated, but you see that there's an e and an ln, right? So that means something can cancel out some way. Well, if you guys didn't remember anything from Algebra 2, you should at least remember this rule of logs, natural logs and logs, where if you have a coefficient of a natural log, this could actually come up to the exponent of the x. So if you have a negative 2 natural log, this negative 2 can come up here. So you could have natural log of x to the negative 2. So this negative 2 would actually go inside here, like that. I don't know why that works. It's the way it is. So I'll actually, instead of erasing stuff, so no one has any questions later, I will write that. So e to the natural log of x to the negative 2. All right, so now we have e to the natural log of something. That means this can cancel out. The way I like to think about it is, the way I don't forget that, is if suppose I literally drew a line to try to cancel out the e in natural log, the negative 2 would be in the way. So this would be blocking it. So therefore, I would remind myself, because of that, this negative 2 needs to be brought up to the top. So that's a good little mental association I have with this rule. So now that the negative 2 is on the top, cancel that out. Our mu of x is going to be equal to x to the negative 2. OK, so now we're basically done. If we were pressed for time, we could put everything in there and find the answer. But I'm going to go through it in one extra step. All right, so the next job we need to do is multiply this mu of x by the entire original equation, which is not going to be this, but is going to be this. Very, very similar, but this one, because this is in the linear form. I think I could have moved that on the bottom, and I could have rearranged the board differently, but whatever. I'll just go up like that. OK, so we'll multiply mu of x to the negative 2 times dy dx minus 2y over x equals our x to the negative 2, because you need to multiply mu of x by the entire equation, our x to the negative 2 times x squared, look, you see that cancels out, times the cosine of x. So as you can see, the negative 2 and the 2 are going to cancel out, so that's good. A lot of times, you have something cancel out on the right side with your q of x. All right, so that's good. Now we have this left side where you have the mu times the whole thing. So this, I'm going to do something weird. I'm just going to go like this. I'm going to go right there. All right, so from that left side, we can just say the association that just like we did here, the left side of this equation times mu is equal to the derivative of mu times y. So let's do that. So we literally just write derivative in terms of x of mu of x times y, just like that. And this is going to be equal to whatever is left on the right side after you multiply it by mu. So we already multiplied it by mu, which gets this cancellation of the x squared. So we're just going to end up with cosine of x. All right. Any questions up to this point? No? Good. Good. All right. So next step, integrate both sides. Integrate both sides. Should I go faster? You guys getting? Yeah, you guys are getting this. I can tell. You're losing interest, but whatever. OK. So take the integral of each side, so you end up with mu of x. I don't know why I just wrote mu of x. I'll just write x to negative 2. So x to negative 2, just like that, equals the integral of cosine. Integral of cosine is going to be sine. So this equals sine of x plus c. And then we have, it's going to be a little sloppy here, but then we have our x to the negative 2 times y equals sine of x plus c. So that means we divide this whole thing by x to the negative 2. And this is going to be our answer. But we have an initial condition. So we need to quickly, we could do that, plug in that initial condition. I need to get an eraser. All right, let's go right here. So whatever equals x. All right. OK, so we're going to go right here. So we have our initial condition that pi, or that y of pi is equal to 2 pi squared. So this is going to be what y equals. So we can put in that y is going to be, so now 2 pi squared is going to be equal to the sine of pi plus c over x to negative. Well, since we have divided by x to negative 2, we could bring that up and multiply the entire thing by x squared. That's the same thing. OK, so sine of pi, according to the unit circle, is going to be 0. So this goes away. So you have 2 pi squared equals c x squared. And what's x going to be? X is going to be pi. Yeah. OK, so it's going to be pi. So pi x squared. OK, so that's really easy. From that, c is going to be equal to 2. Yeah. So c equals 2. OK, so there we're done. Wherever we see a c, we're going to put in a 2. And that's your answer for exact. All right. All right, for linear, sorry. So is there any questions on that at all? OK. Now I'm going to go on to Bernoulli. So that's probably what a lot of you guys have been waiting for, because that's a little tougher. All right, so I'm going to bring that board down, or whatever. I'll bring this one up and leave it up, and then just use this one. OK, because linear and Bernoulli have a lot of similarities. So now we're almost done. OK, before I start, is there any question? No? OK. Before I start, I want to say that if you guys know Bernoulli already, like really good, and you guys can just get any Bernoulli right, don't really pay attention to my method as much, because mine's a little different. I think those of you who've been to my reviews before, I've said that before about Bernoulli. It's a little different, because I do, when you put this v, there's like, you get v equals y to the 1 minus n and everything. But then once I do, the stuff I do from there is a little different, because I find different variables, and I plug it in differently. But if you guys are a little lost, maybe you want to pay attention to this method, because it works every time. And to me, it makes a little more sense. But to others, it doesn't. That's just the way I learned it. And I never bothered to learn it the other way. So, OK. So a Bernoulli is similar to a linear. The idea of a Bernoulli is really to manipulate it with a v instead of a y to get it to look like a linear. Then you can solve it just like a normal linear. So that's really what we're doing. When we're doing those, that process where you have the v and everything, that's what we're doing. We are making it look like a linear. We're modifying it, if you will. Bernoulli has 2 L's. I found that out like a month ago. OK, so it looks like this. It's going to be very similar to a linear, but a little different. So same thing with the q of x, but then you're going to have a y to some power on this side. It could be y to negative 1. They could disguise it, put like 1 over y, which is still y to negative 1. They could put in y to the 5th, whatever they want. So if you have a y on this right side, it's going to be a Bernoulli. Another thing they can do, I just thought about this now. Suppose they put a y in the front, and they wanted you to divide it out by every side, by both sides, divide it out through. Suppose you had like a y squared here, and like a y in the front, and you're like, oh my god, it looks Bernoulli, but I don't know what to do. So you do the same thing as you do if there was a coefficient in front of the linear, and divide it out. You end up with a y here, and then you end up with a y to some power on the right side. Therefore, you know it's a Bernoulli. All right, so that's what it looks like. I'm just going to go through with an example. All right, so what do we got? All right, so we have example dy dx equals 5y minus 5t y cubed, and that's it. OK, cool. All right, so we have that. Is it in the form of our Bernoulli? Not exactly. We've got to move some stuff over. We have a dy dx, that's good, plus p of xy. Well, OK, we have a y cubed here. OK, sorry. I realized that right now. I'm like, oh, I always mess it up. All right, we'll make them x's because I'll write x's. OK, so we have dy dx. I think I wrote it that way in here. Oh, I wrote it that way in here. Wow. OK. For those of you who have the notes, just t's and x's are the same thing. Not yesterday, just today, to confuse you a little more. OK, so we have this. Since we want our p of x to be next to just a y, we're not going to use this term for our p of x. We're not going to move this term over. This is going to be our q of x times y to the n, which is pretty apparent there. So we're going to move this 5y over. So you have dy dx minus 5y equals negative 5x y to the third, just like that. All right, so now it's in the form of our Bernoulli. So that's good. Next step is to, OK, so our next step is we need to turn this thing into a function instead of x's and y's, v's and x's, in order for it to look like a linear equation where we could solve it normally, and then we could use those associations that we made and transform it back to x's and y's. So the first step we're going to do is we're going to make v equal y to the 1 minus n. And we're just doing that. Why? Who invented this? Again, I don't know. I don't know the theory behind it, but that's just the first step of what we're going to do to transform this. So v equals y to the 1 minus n. So n, according to our original template of what our Bernoulli looks like, is our our degree of the y. So our degree of the y right here is 3. So I'm going to write right here, or right here, n equals 3. N equals 3. I don't know if I should have, whatever. N equals 3. OK. So now from that, v is going to equal to y to the 1 minus 3, which is going to be negative 2. OK. Now some people from here, they derive it in terms of v, like v dy or whatever. But I do it a little differently. The way I do it is I try to find y first, because I like to find y first, because our idea is we need to plug in everything for y and then plug in everything for dy dx. So we're going to plug in something, like we're going to plug in something times dv dx here. Then we're going to plug in for here, we're going to have our association with y equals something with v, which I'm going to find right now. And then here you do the same thing. So you're literally just finding everything you need to plug in from v's, or from y's to v's. All right, so let's do that. So here you can say that v equals 1 over y squared. And then from there, if we move this y over here, move this v down here, take the square root, y equals 1 over v to the 1/2. Or you could just write 1 over square root of v, or v to the negative 1/2, whatever way you want to write it. It gets a little intense with the fractions, with the exponents and fractions. But if you follow it through and you do it right, everything's going to cancel out and look nice. All right, so we have this association. This is important. We're going to use this later, and we're going to use this directly to plug into this y and this y. All right, so now the next thing we need to find is our dy dx. All right, so we have y. We can find dy dv. Let's do that right now. If you go right here, dy dv is going to equal to, if we take this up, v to negative 1/2. This is going to be negative 1/2 v to the negative 3 over 2. So it's, like I said, a little complicated with the fraction. I think the other way you do it, it's also like this. So whatever. So you end up with that. So we're not looking for dy dv. We're looking for dy dx. So to get that to look like to be dy dx, we can simply just multiply it by dv dx. This is where it's not conventional what I do, but it works. You literally just like out of thin air, I'm multiplying it by dv dx. Because as you can see, the v's cancel out, and then you're left with dy dx equals something times dv dx is what we're looking for. Yeah. Yeah. Or you could even think about it like implicitly. Once you find this derivative, you take the derivative of v in terms of x now. So it's going to be that, and you multiply it by dv dx because you don't know what that is, and then multiply the other side by dv dx to make it equal. Does that make sense? Kinda? OK. If it doesn't, if you have any technical questions, you could ask me later or whenever you feel like it. I don't know. So you have this. So now we have this is going to be equal to dy dx because these cancel out. And we're going to plug in this whole right side into our dy dx as well as our 1 over v to the negative 1/2 into this for y. OK, so let's do that right now. So dy dx is going to be equal to, all right, on the top, negative 1/2. All right, 1 over v to the 3 over 2 times dv dx. And then it's going to be, what do we have? Minus 5 times y. So y is going to be 1 over v to the 1/2 equals negative 5x times v times y cubed. So that's going to be this thing, 1 over v to the negative 1/2 to the positive 1/2 cubed. So that could be simply written as 1 over v to the 3 over 2. Because if you cube this entire thing, you'll have 1 cubed, which is 1, v to the 3 over 2. OK. So now we have this. So now our next step, once we have this, the hard part's done. We need to make this look like a linear. This is very, very close to a linear. What we need to do is the same thing we do to find our normal linears. We find if there's a coefficient. We multiply this coefficient, or you multiply it by something, or divide it to get rid of this coefficient. Here, I'm not going to divide this by every side. It just looks weird. You could multiply this entire equation by something to have this cancel out. So you could literally just undo this. You're dividing by 1/2, dividing by v to the 3 over 2. You could just multiply it by the opposite of that to get rid of it. So I'm going to multiply this entire equation in order to get rid of this coefficient by negative 2 times v to the 3 over 2. So I came up with that because the coefficient of this, it would just literally undo it. So negative and negative would cancel out. V to the 3 over 2 would cancel out with this. The 2 would cancel out with this 2. All right? That makes sense? All right, cool. Yep.
Where did on the right, the 1 over v to the 3 have?
This came from the, so right here we have y cubed. Oh, his question was, where did this question was, where did this come from? The 1 over v to the 3 over 2. So this came from the fact that in our equation we have y cubed. And we have our association with y is that it's 1 over v to the 1/2. So once we plugged this into here, we are, in essence, cubing this entire thing. So if we cube that, you end up with, on the bottom, instead of 1/2, 3/2. OK, cool. So once we're doing that, once we multiply this whole thing, this factor that I'd made to undo this coefficient, multiply it through, we'll see what happens. So this obviously cancels out the beginning. So you have dv dx. OK, so now you have negative 2 times negative 5 plus 10. V to the 3 over 2, 1 over v to the 1/2. So v to the 3 over 2, v to the 1/2, that's to cancel out to just be v. So 10v equals negative 2 times negative 5, positive 10. X is going to stay the same. And you have v to the 3 over 2. V to the 3 over 2 on the bottom, multiply that through, you're just going to end up with 1. So that's it. Now that looks nice, right? That's a nice linear. If it doesn't work out to looking like this, if you still have some weird v on this side, then you probably did it wrong, and you need to go back and retrace your steps. OK, so now here it's a normal linear, and we just solve it normally. So the thing we're going to do is we're going to find our integrating factor. Or first we're going to find p of x is equal to 10. Integrating factor mu of x equals e to the integral of 10 dx. Which is going to be e to the 10x. OK, are there any questions from here to here? That's like a big step. No? You good? All right, cool. All right, so once we have an integrating factor, we're going to use that and multiply it by the entire thing. I'm going to skip a little bit of steps here. So multiply the integrating factor by the entire linear equation. Don't go back to the original equation yet, because we're not there yet. We're dealing with v's and x's at this point, just v's and x's. So multiply that through. E to the 10x times dv dx plus 10v equals to 10x, like that. So now we can say this entire left side of the equation is going to be equal to the derivative of mu of x times y. Just like I said before, and I always remember that for Bernoulli and linear, that the derivative, or the left side of the equation, once multiplied by mu of x, equals mu of the derivative in terms of x of mu of x times y, or v in this case. Yes?
Why is mu of x just 10?
Because it's everything in front of, in this, or the y, or in this case the v, because we flip-flop v and y. Oh, it's okay. Yeah, q of x is 10x. It's just 10x. Okay. Okay. E to the 10x. All right, we got that. Boom, boom. Okay. So now, like I said, make this derivative in terms of x of mu of x, which is e to the 10x times v, right? Yeah. Equals e to the 10x times 10x. All right. So now we're going to have to integrate both sides. So once you integrate that, the integral of a derivative cancels out, and you're left with e to the 10x times v on this side. And the integral of this, we're going to have to do some integration by parts. But I am going to do it the fun way, my tic-tac-toe way, where I do it in 5 seconds. All right. So, because I didn't do this yesterday, I'm dying to do it. All right. So what I do is I set up pluses and minuses. And the idea is I put in, there's two terms here, right? There is e to the 10x, and then there's 10x. Or you could just put x. You could take that 10 out. So I'm going to write this integral down right here so everyone knows what we're doing. So e to the 10x times 10x dx, just like that. All right. So now I'm going to put in a term that I can derive all the way down to 0 on the left side. So by that I mean 10x, for example. Derivative of that's 10. Derivative of that's 0. It derives all the way down to 0. So I'll put that right here. So 10x. Then I'm going to derive it to 0, 10, and then 0. So we don't even need this column. Actually, maybe we do. I don't know. OK. So then the other term, this thing, we can integrate this many times, and fairly easily. So e to the 10x is right there. So e to the 10x over 10. It's the integral of that. E to the 10x over 100. Those are the integrals. So now all we do is do this. Boom, boom. That's it. Then we're done. That's really cool. If you guys want to learn that later, like actually learn it, I'll teach it to you. But if not, the way to do it is you do, this is going to be your u, this is going to be your dv, and then you find du and then find v and then do ultraviolet voodoo or whatever that thing was. OK, so our next step here, we multiply these together. So we have positive 10x. I'll go down here. So positive 10x times, we ignore this negative sign, so positive 10x times just this. So e to the 10x over 10. So now we have minus 10 times e to the 10x over 100, and then plus c. OK, so this is going to be our thing. So this 10 cancels out, this cancels out, this 10 cancels out, this 10 cancels out. So we end up with x times e to the 10x minus, what do we have left with? E to the 10x over 10. OK, so this is going to equal v. Did I mess up? Or no? Wait, where? Did I mess up? Or
The left half of that.
left half of this?
I mean, on the right, earlier on, all the way over there, yeah, you have to get 10x times 3.
Oh, yeah. OK, good. OK. Yeah, so I made a mistake here. Yeah. Yeah, because I just had it equal to v. So we have here, remember the left side here, once we integrate the derivative, we have e to the 10x times v. So we still have to have that. So e to the 10x times v. All right, so now we have this. Now we're going to divide e to the 10x out. And this board's getting messy. Yeah, plus c is still there. See, it's getting messy. Hold on. C equals e to the 10x times v. All right, so I'm going to go. I'm going to go over there. It's the only open spot I could find. Yay. Hope the camera can get that. So I'm taking all this stuff and I'm pushing it somewhere else. All right. All right, so we're taking that. So now we need to find v. We're going to find v, and then we're going to put in this association back into, so we can find a relationship between y's and x's. So we could divide e to the 10x by both sides. So we end up with x minus 1 over 10 plus c over e to the 10x. Now since that's a common thing, that because we're dividing c by a function that changes with x, we have to put, it's not just another constant. It changes with a variable. So suppose we had we're dividing it by a number, dividing it by some other thing, then we could just leave it as c or make it some other constant. Here we can't because we're dividing it by a living function, whatever that, it changes, dynamic. All right, whatever. Let's say a bunch of words. All right, so it equals v. So this equals v, right? Are we done yet? No, almost done now. So this v, we know that this v is equal to y to the negative 2 or 1 over y squared. So we can get rid of this v, put in 1 over y squared, multiply this by this side, divide this entire thing, put that on the bottom, take the square root of both sides, and then you're done. So once you do that, the whole thing, do the stuff, y equals the square root of 1 over 10, and no, you don't have to simplify this, c e to the 10x. That's it. Yay. OK, that's it. Wait, I forgot something. OK, so x minus 1 over 10 plus c e to the 10x, just like that. So this is your answer. And if you had initial condition, good luck with that. You have initial condition, you try to find c somehow with x's and y's. Yeah. All right. Any questions with that? I know it was kind of, yep.
To find an initial condition in this case, could we do it earlier?
So,
Before it gets ugly like that?
OK, so the question was, can you use if we had an initial condition, can we use that initial condition earlier in the problem so we don't have to figure this out? If we used it, where are you saying?
Like in the box part over there, if we just plug in y to the negative 2 there and solve for c.
Yeah, you could. You could. So you could take this v out and then put in y right here if you had an initial condition and solve it. But I mean, I think it's equally difficult because you might get thrown off here. You might not put back the v or whatever. It might get a little complicated. So the way I would do it is rather have the complete answer and then just find c later. But whatever's your preference. OK. Any other questions on Bernoulli in general or anything like that? No? Are we OK with Bernoulli, or should I do another one? No, we're good? OK. You guys ask me questions later. We're almost done. We're literally 10 minutes. Yeah, exactly. So what we're going to do now is we're going to simple homogeneous just to refresh your brains a little bit if you forgot the exact term. I'll even go over. I'll do Cauchy Euler tomorrow. OK, so I'm going to take this board down. All right. Anybody have the time? OK, cool. Good. All right. Whatever. I don't even have everything homogeneous. All right, so homogeneous. So very easy. So what you do is you have a thing. Y double prime plus, this is second order. Y double prime plus, I don't know, what works? Y. 2y. Prime. Y. No. Sure. Whatever. Equals 0. Yeah, that works. All right. So suppose you have a thing like this, right? So this is a second order homogeneous. You might have something on the right side, which we'll talk about tomorrow. That's when we find out particulars with undetermined coefficients, variation of parameters, and all that good stuff. So the first step of all of those second order problems is to find the homogeneous equation. So for that, we literally just turn it into r's. So our derivative degree, whether it be second derivative, first, or 0, is going to be our r degree. And then you have 2r plus 1 equals 0. So this is going to be r plus 1 squared, like that. All right, so this is an example of 2. So you're going to have r equals negative 1. So this is an example of one real root. There's 3 cases where you have 2 distinct roots, which are different, which is 2 different roots. 1 root that's the same, that happens twice, which is just r plus 1 times r plus 1, which is going to be r equals negative 1. Or where you have 2 complex roots. So if you have, so the answer for this one, since it's one root that's the same, you'd have yh equals c1 e to the negative t plus, or x, whatever you want to use, plus c2t, or x, e to the negative x. All right, so just like that. So the first case, I always write down all the case. I should have done that first. So case 1 is when r equals 2 roots. So 2 roots could either mean like simply like two numbers, 1 or 3, or it could mean plus or minus a certain number. So if you have the answer to be plus or minus 1, then that's considered 2 roots, not 1 root. So the answer for 2 roots would simply be the homogeneous equals constant 1 e to the r1, which is the first root, times your variable x or t, plus c2 e to the second root times x, just like that. All right. So case 2 is when your roots equal 1 identical root, or 2 identical roots, because you can have 1 identical thing. I don't know. So 2 identical roots, which is just something like this, where you have plus 1 or minus 1 or plus 1. You have 1 number. That's the answer for both monomials. So if that's the case, then your homogeneous is going to look like c1 e to the r x plus c2 x e to the rx. The reason why you have that extra x is because if you didn't, both of these would be able to go together, or they would be similar to the effect that c1 and c2 there'd be nothing different, nothing to distinguish the difference between c1 and c2. And if you had a third root that's the same, you could just add plus c3 x squared e to the rx. So you can kind of see how there's a pattern for as many roots as there are identical roots there are, whatever. So I can't even speak. All right, so that's the case 2. Case 3 is when there is a complex. So r equals complex root. And the complex root is in the form of r equals alpha plus or minus beta I. Like that, where I is imaginary square root of negative 1, I. All right, so r equals that. So the way you find r is when you try to factor this and it doesn't work, and you end up with having to do the quadratic equation. And you end up with doing the quadratic equation where you end up with the square root of a negative number, where you have complex. All right, so the homogeneous for this case would be e to the alpha x, which everyone forgets, because a lot of the times in eigenvalues and all stuff, you have alpha is going to be 0. So you always have like the answer is plus or minus something I. Here, the real form of it is alpha plus or minus beta I, where alpha goes into your e to the alpha x. Most of the time this is 0, so this term becomes 1, and we don't have to worry about it. But it's still there. So c1 cosine of beta x plus c2 sine of beta x, just like that. All right, so that's basically it. Should I do an example of that, or I think you guys are good? Yeah, I think you guys are good. I'll do more of it tomorrow for eigenvalue. What are we doing tomorrow? undetermined coefficients and all that stuff, variation parameters. I'll be there for that. So tomorrow time is 5 p.m. right here. I made it a little earlier because it's Friday. I don't want to ruin you guys Friday night. So that's it. Yeah. Thanks.
So we got an hour. Think we can make it to Chipotle and back or nah?
Fuck yeah.
Afterwards.
But we can do it after. If he's online, do you want to?